This Happy Maths Hour show is all about mystic roses, symmetries, people maths, geometric and numeric patterns and sequences.
I used this in school more than 30 years ago. I don't claim any credit for it, really, but I have certainly developed different ways of using it. So, hello, everybody. Now, there's a lot of visualization in this. You have a mystic rose. And Caroline, you're going to describe it. And this is what we ask the children to do. Typically, in a lesson, we would have a poster or a large copy of this. And we'd sit a child, this works for all ages, in front of it, and we'd say, now tell us what you see. Tell us what you see, Caroline.
So what I see looks like a circle. Well, actually, it almost looks 3D. It looks like it could be a ball or a sphere. But the edges are not, it isn't an actual circle because all the edges are straight lines and they're joining these beautiful fan-shaped points. And let me see, how many are there? 2, 4, 6, 8, 10, 12, 14, 15. So it's a 15-sided polygon. It's got 15 edges on the outside, but then there's another, it looks like a circle in the center. It's quite a small circle. It does look like a circle, but I'm looking at it, and again, it seems to be made up of lines, but there is a hole in the middle where there are no lines.
Yes, you're talking about lines. Tell us more about the lines, Caroline.
So every line joins 2 points. So these fan-shaped points, every line that I see,
Caroline,
goes from one of those
you
points
mean
to another.
Caroline, you mean the lines form a fan? The points, well, they are sort of fan-shaped, I have to agree, but points are
like
dots.
fans. Yes,
points are too small to see even. These are splurges that are where the points are somewhere.
So lines join 2 points on this polygon.
Somewhere inside that area that is blackish, where all the lines meet. And there are lots of lines meeting at each point. How many, Caroline? You don't need to count them. What can you say about the lines?
I've counted 15 points, so I'm guessing that there are 14 lines.
Let's leave it there for now. Each line joins
to every point.
other point.
I'm looking at one, it goes there. Yes, this point that I'm looking at definitely joins to every other point. So, and they all look the same. So I'd say I would say there's
don't
symmetry
say how
there.
many. We want people to work it out for themselves.
I can see symmetry, though. I can see symmetry.
Ooh, lots of symmetry. Okay, let's go on to so the questions are, what do you see?
Oh my goodness, I can see another circle as well. It looks, well, not the circle. It's made up of straight lines, but it's like another concentric shape further out than the center one.
Wow, this is wonderful, isn't it? So as Caroline describes it, she's coming out with more and more things that she sees there. And those of you who are able to see it will see some other things possibly. So we're asking everybody to describe this design. And then this is the question: how would you draw this design? So, well, we're leaving that as a question for everybody to think about, but it's a good question. How would you draw it? And then how many points on the circumference of the circle? Caroline's already given you the answer, which is 15.
Sorry.
No, that's fine. That's fine. Now
wait, how did you do this? Because this one has lines going right through the center.
Yeah, so this is a different
one. It's different. Oh.
It's a different mystic rose. So what are the similarities and what are the differences?
Well, the difference is that the lines go right through the center. There is no hole in the middle, although there is like a piece of cake or a piece of pizza in the middle, where you have what looks like a circle that's divided into equal parts, but they all join in the middle. And also this one is different to the other one in that somebody's drawn a circle round it. Yes. An actual circle round it.
Yes, yes. And so what you have is two edges of the outer polygon. There's lots of polygons, but the outer one, two of the edges are joined from each point, but they're not the outer boundary. There's a circular boundary right on the edge. This is subtly different, but important differences from the last one. So we now ask the question, what do you see now? And we ask people to describe this design and how would they draw this design and how many points on the circumference of the circle. Now, this is different. So how many points this time? As Caroline remarked, now we have what are called diameters. A diameter goes through the center of the circle, and we didn't have any diameters in the last mystic rose, but this one has got diameters. So there must be an even number of points, and it's actually 16.
Well, I think it's a hexadecagon.
Okay, that's a fancy name. That's a fancy name. Okay, now the picture shows you two mystic roses. In fact, they are the same ones.
The same two. Okay, right.
So now being able to see them side by side, you can see if you're looking at it, the similarities and the differences between the two mystic roses. And you may be thinking, oh, well, okay, so what's special about them apart from the fact that they're pretty patterns? I'm
wondering if even numbers always have the diameters going through and the odd numbers always have the circular shape in the middle.
And Caroline, you mentioned symmetry. There's a lot to do there with symmetry, isn't there?
Well, weirdly though, I can really clearly see the symmetry with the odd number of points. I can also obviously see the symmetry with the even number of points, but I find it counterintuitive that there's so much symmetry with an odd number of points, but I can see it very clearly.
Isn't it lovely? Yes. So when we show this, we say spot the differences and ask how many points on the circumference of these circles. And we've just discovered that there are 15 on the one on the left and 16 points on the edge of the one on the right. So there's something definitely different between the odd number of points and the even number of points. And then, of course, that one needs to ask, is that difference going to occur with different mystic roses, with different numbers of points on the edge, but is it going to depend on whether they're odd or even? What do you think, Caroline?
I didn't actually fully understand the question, I have to say.
Let's repeat the question. Sorry. We've seen two different mystic roses. So one's got an even number of points on the edge, one's got an odd number of points on the edge.
Yep.
We've seen differences, and the question is, does the difference we see depend on whether there's an even number or an odd number?
I just had a burning desire to start colouring in all the similar patterns so that you could really be able to see. I think it would really highlight the similarities, the differences, and the symmetry, and how many identical patterns there are in each of them. I just wanted to get my colouring pens out then.
Brilliant, Caroline. Well, what you see on this slide is an 8-pointed mystic rose, so it's an even number. And this would be lovely to colour in, wouldn't it? Because it's a little simpler than the ones we saw before, and especially for a younger person to colour in. And you can see the symmetry here. And the question we just asked before the break was, does the symmetry and does the sort of pattern that we get depend on whether there's an even number of points on the outside, like this one, or whether there's an odd number of points? So we'll leave people to think about that, shall we, Caroline?
Yes, I'm just looking now because you've got one that looks like it's complete where you've joined all the points, and then you've got the smaller one to the left. where
Ah,
you haven't joined all the points.
exactly. That's where the people maths comes in, because it isn't a mystic rose on the left, okay, but it's like a mystic rose. So we might think now, what's the same and what's different about the two constructions? So there are similarities because there are points on the edge of a circle, and the points are joined with chords. But
it's part of a mystic rose.
It is, isn't it? But in the one on the left, which is called a Poncelet circle, and we call it, we have we have a more sort of fancy name for it, don't we, Caroline? We call it these pictures like the one on the left, the path to the stars.
I love that name. We've got a whole workshop based on Path to the Stars, and Toni writes these amazing resources on the Aiming High website. And if you are inspired by any of this, in fact, let me start with my ticker tape. And you want to follow any of this through, go to the Aiming High website. I'm going to put the link is in the description. The link to the Path to the Stars activity is in the description. All you have to do is click on it to go to it, and you can join the Facebook page as well. Join, what's the Facebook page? As every single day, Toni puts on an activity, just a moment, just a starter, just a little maths moment, a math starter.
People maths. What's people maths? Well, it's where people get up and move around and use their bodies and do something, actually physically do something. It's not sitting down with a, pencil and paper or pieces on a table. It's actually getting up and physically getting involved, like the people you see in the photo there. Now, what are they doing? They're holding string, but they started off with a ball of string and they stood equally spaced around a circle, and there are 8 of them, and they're making the shape that you see in the picture diagram below. And then the first person passed the string across to somebody on the other side of the edge of the circle, but it wasn't the next person to her or the one next to along. It was 3 places along. So can you see how the string goes around? It goes from one person, then it misses out 2 people, and it goes to the 3rd person round. It keeps on going until it gets back to the beginning, the person who started it. And that's what we call one of the paths to the stars. And the paths to the stars are in these Poncelet circles. And the circles are, 8 points around, so it's an 8-3 Poncelet circle. And it's an 8 because there are 8 points on the edge, and a 3 because it's every 3rd point round that's joined up. Now, what's the difference between that and the mystic roses?
What I can see is that it follows the rule of you can draw that shape without lifting your pen off the paper.
Yes.
So it's a continuous path. Whereas,
and it only joins a few it only joins points, but it doesn't join every point to every other point.
It doesn't join every point to every other point, but it joins, all the points are joined together, but via other points.
A path to the stars.
Path to the stars. And if you get back to the beginning and you continue, you just keep making the same shape again and again and again and again, which means that to make the mystic rose, you then have to create a new path. And you've also, with the mystic rose, you're actually following the path all the way around the outside.
But you see, there are lots of paths that start with one point and come back to it. In the mystic rose, there are triangles.
Yeah.
There are quadrilaterals and
squares. Oh my goodness, of course. Of course it's a regular shape. So
isn't it beautiful?
Oh my goodness. There are how many squares? Oh, well, there's 2 squares.
So we
Oh my
were,
gosh, you can put all kinds of different shapes within it.
yes. So in the beginning, we ask people to, what do you see? And they can describe a lot of things that they see, but it takes a while to see all the possibilities. It's a rich pattern with a lot in it. Now, this is people maths. So with a few people and a ball of string, you can make your own mystic rows. So it's like the people you saw in the photo on the last page, but here we've got people around the edge, 2, 4, 6, 8 of them, and the lines, which you can imagine doing this with a piece of string. So if you've got 8 of you and a long ball of string, you can make your own mystic rows.
So can you actually do that without cutting the ball? Now there's a...
Oh yes,
I hadn't thought about that. So it is still a continuous path.
It absolutely is, but it revisits some of the points more than once.
And then you go a different way. Instead of going back the way you came, you go towards a different person or a different point.
Yes.
Oh my goodness. So it still is one ball of string.
Yes. And it's not like the path to the stars that we talked about before, because that was only... you know, in the last one we saw, it was going to every third person round. But this time, every person has a piece of string going from them to every other person.
So you have a set amount of people that you skip, so you always go to the third person, whereas this one, the rule is everyone has to be connected to everyone.
Yes, you can see I've put it back to the previous slide, and you can see the difference. Okay, so you might want to do this with, if you get 8 people together and a long ball of string, it's a lot of fun. And you can see, then you can see a lot of the patterns like. Think about this picture. Now remember, a chord joins a point on the edge of the circle to a point across the circle. And we want to know how many of those chords there are. And we're going to get some number patterns by considering a lot of different mystic roses. First of all, a very simple one with 2 people on the edge, and then another one with 3 people on the edge, and then another one with 4 people, and so on. And of course, we're getting lots of geometrical patterns, but the question here is, what about number patterns?
And now we're going to numbers. How on earth do we transition from circles and beautiful, pretty diagrams to numbers?
Well, we talked about people maths and people standing in a circle and passing a ball of string across the circle to make a mystic rose. Well, you can also do this with pencil and paper. So on the left here, you'll see lots of circles, but if you look at them, you've got circles with different numbers of points. So we've got one circle with 3 points on it. The next one has 4 points, then 5, then 6, and so on. We haven't got all the numbers of points possible there, but there are lots of different ones. Okay, and so this is a very, it's a fun exercise for children to do, anybody to do, actually, grown-ups too. And you can join the points as before with straight lines, and you can, as Caroline suggested, you can colour the patterns, and you can talk about the shapes that you make and the symmetries. There's a lot of mathematics in it. So suppose you have 3 points on the circle and every point is joined to every other point. And Caroline, how many lines or chords they're called would that be?
Every point is joined to every other point with 2 lines. I have to say, I was just having a look at something somewhere else for a moment. I wanted to do some jiggery pokery. Is that for the 3 points? For the 3 points, I don't see anywhere else they can go other than to make a triangle.
And that means that there are 3 chords, yes?
3 chords. So the chord being, now I said this wrong, didn't I, yesterday? The chord being, or this morning, a line that connects 2 points on a curve, and in this case, the curve is a circle.
Yes, that's exactly right. It's usually a straight line. Okay.
A straight line, sorry.
Yeah, it has to be
a straight line that connects 2 points on a curve, and in this particular case, the curve is a circle.
Yes, it's a chord. Not a musical chord, a mathematical chord.
And it is spelled the same. It's ch with a ch chord.
Indeed, indeed.
No. And yet we're using chords. We're using physical rope chords to create chords.
Oh yeah, but that's spelled differently. That's amazing.
That's the quirk of the English language.
No. So what about 4 points, Caroline? How many chords for 4 points? Can you? Well, everybody can. You don't actually have to see it. You can imagine a circle with 4 points on it, and every point is joined to every other point. So how many will that be? How many chords will that be?
So I'm cutting a pizza into 4, but I'm also slicing off the curved edge of the pizza. So that's 1, 2, 3, 4, 5, 6. That's what I can see.
Yes, 6 lines.
2, 3, 4, 5, 6. Yeah. So basically making a square and a cross.
So if you've got 2 people, you can only draw 1 line. If you've got 3 people, Caroline said there was she saw a triangle, and that made 3 chords. If you've got 4 people, Caroline saw a square and 2 diameters, so that makes 6. Now, what about 5? How many?
Somebody's got to eat the crust.
Those bits on the edge are mathematically, what are they? Segments.
Segments, okay.
Of crust.
Segments of crust. Well, if they're cheese filled, then they won't mind. So the next one, okay, so we've got 5 points. And so we're going to make a pentagon, which will be the lines all the way around the outside. So we'll make those are segments. Okay, so they're the crust. That we've cut off the crust. And then we've got to join, that's joined the ones along the outside. Then we've got to join that, that, and that. No, we've done that. Then there's 2 extra lines from every point to join all the others. So, okay. So that's 5, 6, 7, 8, 9. I know I'm missing something here. 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's an odd number. I know I'm missing one, but I know what the answer is, Toni. I'm certainly not visualizing. I'm not visualizing any more than 9. I can tell you that much.
Well, it's actually easier to do it than see it.
No, I'm drawing it now. I've got that. If you're feeling like me, you're out there going, what? Get a pen. I'm doing it on a piece of paper now.
Do you know somebody who was a colleague of ours at Cambridge, and we knew him very well, actually, because he was in the same faculty. And everybody has heard of Stephen Hawking's. And he was, as a young man, he was, as fit as anybody else, but then he had this terrible condition. And after a while, he couldn't move, and it was extremely difficult for him to write, but he did have a special computer which he controlled, not with his fingers, but anyway, that's another story. But what I wanted to say is about visualization, because he was a brilliant mathematician, and most of his mathematics he did in his head without writing anything down. So he had the power of visualization and thinking it out in his brain without having to write it down. Isn't that amazing? That is.
I had a very traditional education. Everything was very literal. And I don't think I really visualized anything. And I never could connect all the when you had to spot all the triangles and you had to work out what the angles were in the different diagrams when you were doing your GCSEs. and I never could visualize it. It was only years later when I started, in my case, I just happened to use balloons, but now I use any manipulative, when I started actually making models of what I was doing. And in order to make the model, I had to visualize it. And so I trained my ability to visualize by making the models. And often I literally had to, making it with balloons, you have to design it in your head before doing it, because it might be something very complex. You need to know how many balloons you need. And so I finally worked out that it's so important to use the manipulatives at a young age. The earlier you start, the better, because when it comes to doing the exams and things that you have to do in life, you actually have the power to see something that's written on paper and visualize what it actually looks like. Make a representation in your head of it, which means that you understand it and you can actually work it out. And oh my goodness, Stephen Hawking, yes. Oh, and being able to, thank goodness he had that ability.
Well, no, I think he developed it. He was obviously
but he did develop it, but I think he also had a very natural understanding of the world around him in terms of the theories that he came up with.
That's true. He was an exceptional person, but I mean, when I teach children, quite often I actually say to them, now close your eyes, and then I describe something to them, and I say, think about it, how in your mind, and then ask some questions about it. And it is a way of developing these powers of visualization. And don't hear it mentioned so much now, but we used to talk about mental arithmetic, and that is calculations that you do in your head. You work them out without pencil and paper or calculator or anything. And actually that's still valuable, because machines do calculations much better than people, but people need to know if they've keyed the right instructions into the machine, and they need to know if the answer's sensible. And so a quick calculation in their mind, in their brain, with approximation, maybe estimation, helps them to check. But actually being able to do the calculation themselves is no longer a skill that's terribly important. Certainly not using all those old-fashioned algorithms. You need to understand the process.
Yeah, the algorithms aren't important, but understanding the processes, understanding that the as you say, the scale of the number, the order of the number that or the answer, or what. For example, if it's going to be a geometric shape, what kind of geometric shape is it going to be? Or what order of number is it going to be? And the other thing is that being able to hold things in your head. So when you do mental calculations, you have to hold things in your head. Well, when I was doing programming, this just is one example, even though you were using a computer, coding, you'd call it in these days, even though you're using a computer, even though you had yourself a schematic, a diagram of the code that you're going to do, so you had little boxes, this box here is going to do this code, and then that box there is going to do that code, and that box there is going to do that code. You had to remember how it all connected together, and you still had to keep that in your head in order to succeed and make a program that worked. Because what would happen is you'd do this and that, and then you'd be doing this and this and this and this. And you think, why isn't it working? It's because you didn't keep something in your head, and you forgot there was a connection, that if you did that, something would change somewhere else. And the detail is important. To keep the ability to keep things in your head. When you're doing a project, when you're working on a problem, anything like that, you can be working on a problem, any kind of problem, like what's wrong with my car, and think, oh my goodness, I forgot, or a recipe even. You have to keep things in your head, and mental calculations are training for that.
My field is education, but I'm married to a mathematician, and most of my life I've spent with mathematicians. And when you see the mathematics that they publish, it looks complicated, and maybe there's not a single diagram there on the whole paper, Turn over pages of the books and there's not a single diagram. But when they actually do mathematics, I watch these people, mathematicians, do research mathematics, okay? And they're drawing diagrams and charts, and they're sitting there with a piece of paper between them, and then, or a blackboard very often, an old-fashioned chalkboard, and they're not, most of the time, they're not writing formulas, they're drawing pictures. They're visualizing somehow what Caroline was talking about. She was talking about it in relation to computer programming or coding. And I'm talking about it as doing all sorts of maths. And it's
that ability to visualize and keep, like when you're doing mental arithmetic, you're keeping, okay, I've got this number and I've got that, and I've got that scale. And then using that later, knowing you have to bring it back and use it later, is that is a skill you have to train. And if you don't train it, you lose it. If you don't use it, you lose it. And I've found I've lost it, so I've got to retrain it.
Now we're going to get back to Mystic Roses, and so we've talked about a few points on the here, or a few people, but now we're going to talk about 100 points. Now, here, you wouldn't want to join all the lines because, well, it would be really tedious to do that. But could you work out how many lines there would be if there were 100 points on the edge of the circle? That's the question, and something to think about.
So we're looking for patterns, and something that occurred to me earlier, that I knew there was something wrong. I knew the pattern wasn't right, but I didn't know what was wrong about it, but I knew it wasn't right. Trust yourself. Trust yourself when you have that instinct that I don't think there's something wrong here. Trust yourself, because keep pursuing it and you will find it.
And the number sequence started with 136, and then Caroline counted the next one, which was having 5 points on the circle. And she counted 9, but she thought, that doesn't seem right. 1, 3, 6, 9. Well, 3, 6, 9 might be a very good pattern, but then the one somehow
messes it up. Now we're looking at how number patterns help you predict, help you now do quite complex maths.
Well, we're going to talk about number sequences in a minute, and we're going to come on to a formula for the numbers of these chords that occur. And the Mystic Rose is this beautiful pattern with points on the edge of a circle and every point joined with a chord to every other point. And we've asked the question, if you had 100 points on the edge of a circle and you were going to join every point to every other point, how many lines would that be? And, well, we're not going to draw them and count them. We're going to think about number patterns and number sequences and work out what's happening and why that is the number that we would get, the formula, if you like. We can get a sort of instructions for finding the number, and then we can put those instructions into or rules into an algebraic formula. Now, there's a table appearing in front of you now, and the number of points on the edge of the circle is on the left. So if you have 2 points, you would have 1 line joining them. If you had 3 points, you'd have 3 lines joining them in a triangle, if you like. If you had 4 points, 6 lines, and we thought about that earlier on. And the sequence starts 1, 3, 6, 10, 15, 21. So the question is, now, we did have an 8-pointed shape, or 8 points on the edge of the circle. And some of you will have already counted the number of lines because we had the diagram up and we were talking about it. So did you count them? Do you know how many it was? Or Can you think of it now? How many? So did you count 28? The next number's 28.
I didn't count 28, but I'm following the sequence, so the sequence would take me to 28.
Why was that? Well, let's start at the beginning, because if you are doing any problem, it doesn't matter whether there's any maths in it or not, and you can't solve your problem, very often a good way to break through is to think about doing a similar problem, but a smaller problem. And if you can think about the key or way of solving the simpler problem, maybe you can do the more difficult one. So we'll look at now how many balls there are here in these patterns. Now we've got this sequence 1, 3, 6, 10. All right. And then what's the next one? Now, how is that pattern of red balls like our pattern of the number of chords in the mystic rose? It certainly starts 1, 3, 6, 10. But what is the feature of this pattern here? What is the essential thing about this pattern? So this is
the shape the numbers make, the shape the balls make give you a clue, don't they?
Yes, and that's true. And when you work with sequences in mathematics, one of the ways you explore the type of sequence, you try and work out what type of sequence it is to find the difference between successive terms. Or what do you add to each term to get the next one? So 1 add 2 makes 3. 3 add 3 makes 6. And what do you add to get 10? You add 4, and then you add 5, and then you add 6. 15 add 6 is 21. And then supposing you add 7, you'd get 28. Now, of course, we haven't proved yet that this will go on working for bigger and bigger examples. And as you go along the sequence, this will continue to work. So there's more, yes, there's more to do. But now can you see why it's triangle numbers that are the key here? Because you've got one red ball, and then underneath, you've got 2. 1 and 2 make 3. And then the third one in the sequence is 1 plus 2 plus 3. And each time you're adding a layer with one more ball on that layer underneath the rest, and you're keeping the triangle shape. Now imagine the next one. And is that going to add on 5 more balls? And you'll get, altogether, you'll get 15. Now, it doesn't take a lot to prove now that you could go on with these triangle numbers forever and ever. Because all you do is add one more each time than you added last time. And you can keep on doing that. So you can make bigger and bigger triangle numbers.
So it goes on to infinity, which is another great thing with maths that we were saying that the other day. An engineer will go, okay, that's it. We have reached the limit of the capability of the machine. So we're going to stop there. That's fine. But the mathematician can go on forever. The mathematician can get their imagination, take them to ever. And not only that, mathematicians like to prove that it's true.
Yes, and you can go to infinity, go when nobody can really go physically.
To infinity and beyond.
Okay, so these sequences, right? So I'm going to have another way to describe them. They're 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4 plus 4. 1 plus 2 plus 3 plus 4 plus 5. And the next one is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Each triangle number is in itself the sum of the first so many natural numbers. Or you could start your sequence at 0 if you wanted to, but we have chosen to start this at 1.
Mm.
Okay, and isn't it brilliant? And triangle numbers, I don't think grown-up mathematicians call them triangle numbers unless those grown-ups are teachers. But we use that number in school because it conjures up this beautiful picture, and it makes it easier to see all the properties of these numbers if you think of them as triangle numbers.
And if you see them on a regular basis, well, the thing is they crop up. And I've only since I started working with Toni that I've actually found, I've heard it, but I hadn't really seen it. But now they come up everywhere. And the good thing about that is that you can spot the number pattern. So you've already got this data bank of insight into the way numbers work. And when you see the pattern starting, you go, ooh, is this a triangle number? And that's going to help you interpret the data of interpret what you're looking at, and recognizing number patterns is really helpful.
Well, this is amazing because in mathematics, of course, in real life, in other things that have nothing to do with maths, sometimes you've got something really difficult that you're trying to do. You know you're going to be able to do it if you're really determined and you really keep trying, but it's difficult. And then you think, one of the ways of solving a problem is to think, have I seen something like this before? Okay. Does this remind me of something I've done before? Seen something about this before? And very often you have. And what Caroline and I are just talking about is that sometimes it's triangle numbers that's the key. And you think, oh, this involves triangle numbers. I know quite a bit about triangle numbers, so let's keep looking, let's keep digging, and we'll solve the problem.
And it can come up from unexpected places as well.
Yes, and that's the thing. I mean, what happens is that you solve your problem because it's really not a new problem, it's something that you've done before, and it's so similar. It could be so similar to the problem you solved before that you've done all the work, and now you've just got to make the connection. And
Toni's husband, who is a research mathematician, he's still to this day makes connections that nobody's ever made before in areas that you wouldn't think were connected, and he's always looking for the connection. That's his almost like a mantra with him. Where's the connection? What else can I connect this with? And that's a powerful problem solving tool.
But it's a way to make learning maths easier for children, for kids, because children find maths quite difficult often, and it's such a shame because it's not as difficult as they imagine. And a good teacher helps you to see those connections. Good teacher helps you to visualize the ideas, whether they're numerical ideas or whether they are geometrical ideas or probabilistic ideas. And to make connections between ideas and put the pieces of the puzzle together and get the answers. And it's
and have fun doing it. It's a lot more enjoyable. It's engaging when you're doing that.
Indeed.
When you're actually intrigued and making those connections. It's like, oh, I made a connection. It brings it. That's all the time we've got time for, because I really want to mention. Go on, Toni.
Can I just mention something else? And that is, last week and this week's, there was a connection between what we did last week and this week. Okay, and next week we'll talk about that.
Right, next we'll talk. And I want to just mention quickly, before we go, that we do have a fundraiser for AIMSSEC, which is the organisation that Toni founded that provides professional development for teachers in disadvantaged communities. And you've got on, you yourselves can use the AIMSSEC Facebook page. Every day there's a thrilling and engaging maths starter, and yeah, it's down at the bottom there. So, and if you replay, you can freeze it and see it. You can join the Facebook group where there's a conversation going on, making maths fun for kids of all ages. We've got a YouTube channel, Maths Toys. We're YouTubers. I'm going to be 60 soon, so we're going to be 60 plus YouTubers.
Oh, and Caroline's going to climb Mount Kilimanjaro to raise money for AIMSSEC as a fundraiser for her 60th birthday, but this isn't for 2 years, actually.
Well, no, you're going to be here. This birthday is the launch of it, because it's the start of my 60th turn around the planet. So I should be doing it for 2 years. You're going to be hearing about it. So
yeah, and
lots
she's
of money for AIMSSEC.
Yeah, and she's already got quite a big group of people are going to join her team to climb Mount Kilimanjaro.
So if you're interested in climbing Mount Kilimanjaro for mathematics to promote AIMSSEC, join us. Thank you very much. We'll see you next week with the connection between the Mystic Rose and Path to the Stars. Was it we did last week?
Handshakes and bows.
Toni, help me here.
No.
Handshakes and bows.
But there was a connection with Path to the Stars. You read right.
There was, yes. Thank you. It was handshakes and bows. Yes, it's all connected. Thank you. See you next week.
Goodbye.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.